Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. To consolidate our knowledge, today we're going to solve a classical kinematics exercise. Then I'm going to prove you one of the usual kinematics equations we haven't proved yet. And later we will solve again the exercise by using this new kinematic equation. So let's start! Alright, so we are going to start dealing with our kinematics exercise. As you can see, the setup is really simple. We have a table over here of 8, which doesn't have friction, but it isn't really important to our exercise. And we have a ball running on it with velocity b, that is going to roll off the table right at time t equals 0. Right? Then it's going to follow a parabolic trajectory till it hits the ground right around here. And we are asked to find the final velocity of the ball right before it hits the ground. The first thing we need to do is to define our coordinate system. And to do so, we'll start by defining our unit vectors. We will define j hat pointing in the up direction and I hat pointing to the right. We also need to define our origin, and we will define it right around here. We'll make the ground to be y equals 0, and we'll make the edge of the table right around here to be x equals 0. And we also define our time coordinate system by saying that at times t equals 0 is when the ball rolls off the table. We are going to assume that this ball is only affected by gravitational acceleration, and we're going to assume that we are on the Earth, therefore it has a value of g. We are going to assume, again, another assumption, that there's no air friction and nothing else, just to keep it simple. Alright, next thing we're going to do is to draw a free body diagram. In this case, it's going to be pretty simple because we are only going to have gravitational force, but it is a good practice to do it in almost all exercises related to classical mechanics. So we're going to do it too. We have our ball over here, and it's being affected by our force, gravitational. Remember, it's really important that you also put your unit vectors in your free body diagrams, so that you know the direction in which each of the forces is. Then we're going to do our analysis of F equals ma in each of our vectorial directions. So we'll first start with I hat, and we can see that in the I hat direction there's no force, therefore force is going to equal 0, and this is going to equal the acceleration in the x direction. Therefore we conclude there's no acceleration in the x direction, and that velocity is going to be constant for all our trajectory. Then if we analyze the j hat direction, we see we have a force over here, and we know that its magnitude is mg because we are near the surface of the Earth, so we can use the approximation of gravitational force. And we also know that it's pointing opposite direction than our j hat vector, therefore it's going to have a negative sign, and this is going to be equal to mass times the acceleration in the y direction. If we divide by the mass on both sides, we find out that our acceleration in the y direction is going to be minus the gravitational acceleration. Alright, now it's pretty straightforward to find our kinematics equation with this equation. But what we're going to do is, instead of deriving it by using some integration, etc., I'll leave that as an exercise to the viewer, and I'm just going to write the equation directly. Okay, so We know that our position in the y direction, that is obviously time dependent, it's our initial position plus the initial velocity times time plus 1/2 of the acceleration in the y direction times. That's the initial velocity in the y direction. This is a general formula you can always derive when acceleration is constant. Then we're going to input all of our data. You know that in this particular case, our initial position is going to be 8. We're at a height of 8. Our initial velocity in the y direction, it's 0. We only have an initial velocity in the x direction. And we know our acceleration in the y direction, it's minus g. Therefore, this is going to be minus 1/2 g times square. Right. So we are trying to find velocity right when we are at y equals to 0. Therefore, to do so, we're going to find time, and then by finding time, we will find velocity. So we're going to input y equals 0 in our equation right over there. So we're going to make this equals to 0. Or if we add up that component, we make that h, it's equal to 1/2 of gt squared. And if we leave the t's alone, we'll find out this is the square root of multiply through by 2h divided by g. You get that? Time equals the square root of 2h over the gravitational acceleration. I moved this result over here to keep space in the whiteboard, and we're going to continue with our analysis. Again, by the definition of acceleration, or of this equation here, by taking into account that it's a constant, we can easily derive the following equation. This is that the velocity, function of time in the y direction, equals the initial velocity in the y direction plus acceleration times time. We want to know the velocity right before it hits the ground. And we know it hits the ground at times t equals 2h, the square root of 2h over g. Therefore, if we input all of the data over here, we will find out the velocity right before it hits the ground. So let's do that. Velocity final, right? That's 0 because there's no initial velocity in the y direction. And we know this is minus g times time, 2h over g. And if we put that g inside the square root, we found out this is minus 2h over g. And note this negative sign. What does this negative sign tell? So we can see that we have velocity in the y direction, and we have defined our positive y direction with our j hat vector to be pointing up. Therefore, this negative sign tells us that our velocity is pointing down, and that is totally coherent with our physical intuition. So we can assume that we're on the right path. What you could do, unit dimensional analysis of this expression and find out that it's actually meters per second. So it seems that our result might be correct. Now we just need to do some vectorial composition to find out the total velocity, because this is just velocity in the y direction. And to do so, we'll know how to do it. This is the final velocity, the square root of the x component is going to be b squared plus the y component, and we have it over here. It's the square of a square root, so it's just the argument, and we have it over here. And this is the result of our exercise. Alright, so we're going to start with the derivation of our new kinematics equation. I left our answer on this setup over here, so we can go back to it after finding our equation. I'm going to use energy principles to derive this equation. So if you don't have the knowledge yet to understand it, you might skip forward to the video and go to where we find and solve again the exercise by using our new equation. We all know that work equals the variation of energy of an object. In this particular case, we're going to assume that our object only has kinetic energy, and that gravity is doing work on it. That way, we can generalize this to situations in which we just have a force acting on us. We all know that, well, this is equal to the variation of kinetic energy we said before. We're going to ignore potential energy and we're going to include it in the work. We know that this is equal to the force times the displacement, definition, and we know that the variation of kinetic energy, it's 1/2 the mass final velocity square minus the initial velocity square, right? And we know that force is mass times acceleration. So, big deal in that. This is 1/2 m minus the initial velocity. Right, so we can cancel these masses over here and we can multiply through that 2 and get that 2 times acceleration times the displacement equals final velocity square minus the initial velocity square. And if we solve for this final velocity, we find out the final velocity square equals the initial velocity square plus 2 times the acceleration times the displacement. And this is one of the classical kinematics equations we all use, but to be honest, I think very few people really know where it comes from. We all know we can derive it by substituting and solving for time in other kinematics equation, but I think this is a more insightful way of deriving it, because I believe it's incredible that this simple equation that can be derived from the other definitions we have about acceleration and velocity, it's really a statement about energy conservation. I think that's incredible. Now we will use this equation to solve again our exercise. Great! Now we're ready to solve our exercise by using our new kinematics equation. And you will find out that now by using this equation it's much easier to do it, because sometimes instead of trying to work hard and just put numbers in the equation and try to get it, you need to work smartly and find the right equations to do something. Lots of times in physics there's going to be multiple ways of solving the same exercise, but some of them are going to be much easier than the others. Alright, so we're going to use this equation on our analysis of the j-hat direction. Remember that before we found out that the acceleration in the y direction was minus the gravitational acceleration. And that's pretty much all we need to know. If we write this equation with our data, we find out that the final velocity in the y direction squared equals our initial velocity in the y direction, that is 0, plus twice the acceleration times the displacement. So we know that the acceleration is minus g, and we know that our displacement, we look over here, it's really minus h, because we're going down h units. Therefore, we multiply this minus. We cancel those negative signs, and if we do a square root on both sides of the equation, we see that the absolute value of our velocity in the y direction, we did the square root of a square number, it's square root of 2d8. And in this particular case, by using our physics intuition, we can see that it must point downward. Therefore, we're going to substitute that absolute value by a negative sign, and we're going to move it to the other side. And now we just do vector composition again to find the final velocity, and it's the velocity in the x direction, that initial velocity we had, plus this component. And as you see, we're getting exactly the same answer, but we are doing much less work. This is all for today. I hope you liked it, and also that you understood that sometimes in physics, it's better to take some time to think about what the easiest way to solve the exercise is, instead of just trying really hard and using the questions you have and doing nonsense sometimes and taking much more time to get to the answer than what you could do if you had the right equations or the right way to do it. Any doubts you have left, you may ask them in the comment section and I'll try to answer them in the best way. Remember to subscribe to the channel and press the bell so that you don't miss any of the new videos. And also, like the video if it was the case. See you another day with more Physicawesome!